All right, so basically we said sine waves are important for a lot of problems. I gave the examples: audio signals, power waveforms, radio waveforms. All those things are sinusoidal, or if they're not, they're sums of sine waves. And so we can treat them as sine waves and do our analysis that way. Okay, so they're really important in a lot of different problems. So basically what I went through is two types of examples over the course of Monday and Wednesday, where I talked about static circuits that have only resistors and dynamic circuits where there's R's, L's, and C's. Okay. So when I have sinusoidal sources, we talked about they've got three parameters. They've got a phase shift, they've got a frequency, and they've got an amplitude, right? Those were the key parameters. Now, if I had a static circuit that had only resistors, in other words, I had a circuit like this, which is a voltage divider. All right. And my input voltage in this case is 10 sine 2 pi 100t. All right, so we'll ask ourselves a couple of things on this. So what is the frequency in hertz on that thing? Sine 2 pi 100t. 100. Guy's got 100 hertz frequency, got an amplitude of 10. Okay. We said with this thing, I got a voltage divider. So if V in is 10 sine 2 pi 100t, V out, which is the voltage across that resistor over there, what's that going to look like? That voltage. What should that look like? So V in looks like this. All right, so I don't know. That's a big question, maybe. I don't know. What is it to say? What does it look like? What's it going to be? Is it going to be a sine or a cosine, or is it going to be neither a sine or a cosine? What's it going to be? It's going to be a sine function, right? And it's going to be smaller than the input because it's a voltage divider, right? So it's going to be a smaller voltage. And we looked at this the other day. Basically, if V in was this guy here, right, which has a 10-volt amplitude, V out, if you do the math, basically has about a 3.3 volt amplitude. All right, the current has a smaller amplitude than that. But basically, in this case where I've got just a resistor circuit, do I even need to worry about this sine 2 pi 100t term that's clogging up my math? No, I don't, right? Basically, the only thing changing in this circuit is the amplitude, right? The amplitudes of the voltages and currents are all related to whatever the resistors tell them to be, right? But the sine 2 pi 100t, all of the voltages and currents have a sine 2 pi 100t in them. So I don't need to keep that term in there. I just need to worry about what happens to the amplitudes, right? Now, we also looked at a dynamic circuit. Now, if I got a dynamic circuit, and this is an RC circuit, we looked at this both Monday and Wednesday. If I have this particular circuit, this is what I get for the differential equation. Now, if that's a differential equation, this thing has two parts to the answer, right? So V out of t in general has what? What's V out of t? What's it going to look like in general? There's a transient and a steady state, right? What's the transient part of it? What's the transient look like? You guys have no idea what the transient response looks like. An exponential, yeah. And it should be a decaying exponential, right? So it's going to be a e to the negative t over tau. All right. And then what's the steady state going to look like? If I have a cosine, in this case, as my input voltage, what's the output voltage going to look like? It's also going to be a cosine. And in general, what we saw is if this guy is 2 pi ft, he's going to basically be a cosine that could be shifted left or right and made bigger or smaller. Okay. So we did this basically at a couple of different frequencies. I changed the frequency f of this input voltage. And I said, let's say it was 0.1 hertz, 10 hertz, or 1,000 hertz. Okay. Now look at each of those cases, right? So at 0.1 hertz, there's a transient response. And I said right here, I can sort of see the transient response going on. But then after the transient's over, basically what I'm left with is a cosine waveform. And what can I tell about that cosine waveform there? What would you say about so I've got basically the input voltage and the output voltage. So back to my circuit here, basically, all right, that diagram may be confusing to you, but I have V in, I have R and C. So here's V out across the capacitor, right? V in and V out are basically both plotted right there. What can you tell about V in and V out here? Same. Steady state, they're the same, right? So if basically V out is just the, looks like to me that it's cosine 2 pi 0.1 t. There's no shift between them. So there's no phi that I add, right? What about here at 10 hertz? The blue is the input, the red is the output. So what's going on here? How would you describe, again, there's three key parameters, right? What are the, so in general, we say that these waveforms have an amplitude, a frequency, and a phase shift, right? Of those parameters, amplitude, frequency, and phase shift, how would you describe which ones have changed on that red voltage? The amplitude has changed and the phase shift has changed. Frequency hasn't, right? The frequency stayed the same, right? The guy's varying at the same rate, but the amplitude and the phase have changed. So it's been shifted, right? In fact, what I said was that this guy lags, the output voltage lags because he's basically shifted farther back in time, or sorry, well, farther ahead in time, I guess. All right. And he peaked. So in other words, like if I look at the time from the peak of the input to the peak of the output, it's happening at a later time. That's a lag. Okay. And he's smaller. Now at 1,000 hertz, he's a lot smaller. And if you look carefully, he's lagging a lot more. He's lagging by 90 degrees. Okay. So the key thing I kind of see there is what the amplitude is clearly depends on what. So here it is for 0.1 hertz, 10 hertz, 1,000 hertz. What does the amplitude definitely depend on? Frequency, right? Clearly, as the frequency changes, the amplitude's changing, right? And the only things that happen, right, we can summarize here. If I have a circuit that only has resistors, frequency always stays the same. The phase changes, the phase stays the same, amplitude might change, okay? With resistors and capacitors, frequency always stays the same. The phase might change, meaning we have a shift left or right, and the amplitude might change. All right, so the key thing is, if with this being the result, there's a way we can simplify this analysis. So basically, to get the steady state solution, we can avoid the differential equation and just find a way to track the phase and the amplitude at a given frequency. And there's a way to do that. And the way we do that is we use a concept called phasors. All right, so we know that to draw a sine or a cosine, like in other words, if I wanted to draw versus time, a sine or a cosine wave, how many points are on that graph? In theory, from 0 to 0.2, how many points are on that graph? Infinite, right? There's a lot of points there. But I don't need to know, to be able to draw that waveform, I don't need to know the value at every one of those points. To draw it, I only need to know the frequency, the phase shift, and the amplitude. So in some ways, there's like a compression sort of way of thinking about this, right? So I could kind of compress x cosine omega t plus phi and get the time out of it and say, you know what, I can always figure out the value of this thing at any given time if I know what the amplitude, the frequency, and the phase are. So this leads to something called a phasor. And basically what we do is we try to track the relevant values of every sine or cosine using this kind of compression idea, basically trying to extract out the key information. Now I'm cheating by just calling this a compression. Yawu can talk about this in context of Fourier and stuff like that, which you'll do in 2254. But I'm going to talk about it just in the context of, from a perspective of a circuit, the only thing the circuit can do is change the phase and change the amplitude. So I'm just going to track the amplitude and the phase. Okay. So I have this guy over here. X of t is 10 cosine 2 pi 10t plus 45 degrees. Now the phasor is basically what this guy is a complex number that reflects the magnitude and the phase of the waveform. All right. So if I'm looking at a waveform that has x of t as an amplitude xm and a phase phi, then what I say is that he has a phasor x, and I put that with a little bar under it. His amplitude is x sub m, and he has an angle of phi. Now that's a complex number, and you guys should recognize this as the polar form of the complex number because you've been doing that with Yawu, okay? I can turn that to rectangular form, but you can see why polar form might be useful now, because when I look at this thing, I can look at that waveform and I can map the waveform right over to the polar form. Much easier than I can to the rectangular form. All right, so let's do that. Let's do an example here. So I want to figure out what's the phasor that goes with this character. So I have 10 cosine 2 pi 10t plus 45 degrees. So what do I do for that? What will be the phasor for that?
10 angle 45.
10 angle 45. And I could convert that to rectangular if I wanted to. Okay, I don't want to. At least not right now. All right, so that guy would be over here, right? So here's 45 degrees, right? Because we measure angle from this is the 0 degree line on the imaginary plane. This is the 90 degree. This is the 180 degree. This is the 270. Or in general, what we often say is this is the minus 90 degree line. All right. This is where this is why complex numbers are useful right here, right? Is because I can basically get rid of, this is what's, it's a little bit weird, right? Imaginary numbers are weird, all right? Differential equations suck. Weird is better than suck. That's basically the bottom line to it, right? Is that we're going to use complex numbers to not do differential equations, right? That's basically what I can do. Is the complex number allows me to track for this waveform the only two things that can change, which are its amplitude and its phase, right? It's a nice sort of compact way of writing that. So we're going to learn how to use that here a little bit today. All right, so let's do some more examples here. So this was for that previous circuit that I was looking at, that RC circuit at the 10 hertz. So my input was cosine 2 pi 100t, and my output is whatever that is, 0.7044 times blah, blah, blah. All right, so help me out with V in and V out. What's the phasor for V in? That
Just one angle thing.
1 angle 0. 10 is the frequency, right? So I would say 1 angle 0 degrees. And then what would it be for V out?
7044.
0.7044 angle negative 47. So basically that would be here for V in. So I label that as V in. And then my V out would be over here somewhere a little bit smaller. And this guy, there would be negative 47 degrees right there. Now, sometimes this is where, when I look at these things, I talk about these things, these phasors leading and lagging each other. And it relates to that sort of time shift that we have when we look at the time domain. All right, so here's the same picture, V in and V out, like that. So what I say here is V in is leading V out, all right? Leading V out meaning that its peak comes at an earlier time than V out's peak comes. That's what I call leading. And when I'm looking at the phasors, a vector that is further ahead in the counterclockwise direction is a leading vector. So remember, which direction is positive angle? Counterclockwise, right? Clockwise is a more negative angle. So something that's farther ahead counterclockwise is leading, right? So we're going to use that terminology a lot, particularly when we get to the stuff related to power towards the end of the semester. I don't talk about it too much when we're just going into circuits. All right, but we'll talk about it later. All right, so V in is leading V out in this picture. Or I could say that V out is lagging V in, depending on my perspective. Okay. All right. So we talked the other day about this. Very often, we always, given the notion of this idea of phasors, we always transition our time domain waveforms to a phasor. And we always do that with respect to cosine, because it wouldn't, you could potentially get something like sine, I don't know, 2 pi 10t plus 10 degrees. A lot of you guys will immediately go in and write this as 1 angle 10 degrees, right? And that's not correct, right? That's not the phasor for it, right? So that's not what I would do. What do I have to do? I have to always get everything into the cosine frame of reference. And there's a trig identity that tells us how to go from sine to cosine. And we talked about this at the very end the other day. So here's sine, the blue, and the red is cosine. I can always shift between them, right? I can say that there's an equivalent cosine to give me that sign. And the way I look at this is when I look at sine omega t, I think, and I look at the picture of cosine, I think to myself, what do I have to do to the cosine to turn it into sine? Well, what would I have to do to cosine to turn it into sine? Like, in other words, if I wanted to make this guy, the red, become the blue, what would I have to do to make the red become the blue? What do I? Yeah, shift it to the right. And in particular, I have to shift it to the right by 90 degrees. And that's what this statement here says, right? Cosine omega t minus 90 is sine omega t, like that. So if I have sine omega t plus 5, there's some angle, then I basically just have to subtract 90 degrees from that angle. All right. So that's something that you'll need to do. I'll ask that kind of question all the time to throw you off. All right. On a test, half of you guys will lose points because you won't pay attention to that. All right. So it's just the kind of trick to be aware of, right? All right. So let's just try 2 quick examples here. So if I give you 10 cosine 2 pi 60t minus 90 degrees, what's this guy going to be for a phasor? 10 angle negative 90. Okay. Now 5 sine 2 pi 30t plus 30. Is that 5 angle 30? No. What do I got to do? I got to turn this guy into cosine. It's 5 cosine 2 pi 30t plus 30 degrees. And again, I got to bring in the minus 90 to make that shift happen. Okay. So this guy would be what? 5 angle negative 60. Yeah. Okay. All right. And basically what it's saying is these 2 waveforms are the exact same waveforms, right? And we're just using a trig identity to write them the same. Okay. All right. So that's going to be important. Now, what I want to do is I want to use this concept to generalize resistance to something called impedance. All right. Which is to say, the resistance is captured for me what's going to happen to the amplitudes in those circuits. And then what's that? Somehow there's some way to generalize what's going to happen to the phase shift as well if there's capacitors. Here. That sounds weird. All right. Anyway, let's start with the simplest type of circuit here. Let's say I've got a circuit with resistors, right? And I want to figure out how to map this thing from the time domain, from what I call the time domain to the phasor domain. So over here, time domain, and over here I have what I call the phasor domain. So notice that in this circuit, what's happening is up here, they're the same exact circuit, but what I'm doing is I'm taking out the time dependence and I'm writing simply in terms of phasors here. Okay. So I know what's going to happen in a resistor circuit because we've already sort of said this. If I had a voltage source V of t that was V cosine omega t, what is I of t going to be in this circuit? It's really annoying. What's Ohm's law going to tell me? How does I relate to V? Well, even simpler than that, right? So you're correct, but if I just said, okay, relate to me I, V, and R, what would that be? V over R. So I of t would be V of t over R, which would basically be V over R cosine omega t. Like we said, this cosine omega t part's the same in both of them. If I do this in the phasor domain, what I see is that let me represent each of these as phasors, right? This guy is going to be what? He is going to be V equal to V angle 0. All right. What's this guy going to be? Well, I guess I could write it as I cosine omega t, like that. And I could say his phasor is I angle 0, like this. And if I look at that, the phasor here is basically what? It's just the amplitude of these things. Okay. And I can see that I has to be equal to V over R. So what I did here is I basically, in the phasor domain, what it says is that in the phasor domain, the phasor for that voltage is equal to R times the phasor of the current. All right, very simple. If I can look at the time domain waveform and get it to a phasor, then I can just use Ohm's law, just like I did before on the phasors and on the time stuff. Okay, same basic thing. Now it gets, and so the whole principle of this is when I'm looking at the voltage and I'm looking at the current, right? They're entirely related to each other. So there's no phase shift between them. All right. And so I'm going to give a general name to what I call this thing here, right? This is the resistance of it. The general name I'm going to give this is impedance. But let's look at that in particular for a capacitor. Okay. So let's say I hook a capacitor up to a voltage source. And my circuit's boring. It's just a voltage source hooked up to a capacitor. So here's V of t. And let's say V of t is equal to V cosine. Let's keep it omega t, like that. In fact, I'm going to give it an angle, phi v. All right, so phi. So in other words, it may be a cosine that's shifted away from 0 degrees a little bit. Okay. So help me out. In terms of what I wrote there, what's the phasor for that? What's the phasor for that? V, yeah, and I wrote it with this phi sub v. I kind of did that on purpose. All right. Now, let's say I wanted to find the current in that circuit. How would I find the current in this circuit?
V over the impedance of C.
Well, you're skipping ahead on me. That is right. Okay, but we don't know that yet. Right? I just use those words. Based on what we know I equals C dV dt. All right. So if I equals C dV dt, can I use that? I can say I of t equals C dV dt. All right, and I won't say V sub C because in this case V sub C is V. Okay. So what do I do? What do I do now? How do I figure out the current? Here's the voltage. I equals C dV dt. What do I do now? Well, I don't want to do an integral, right? I want to figure out I of t. And I know V. So not the integral, right? But I want to do what instead? I do the derivative, right? Right. So C times d by dt of V cosine omega t plus phi v, like that. Okay. So what's the derivative of cosine omega t with respect to time?
Omega or negative omega v sine omega t plus omega.
Okay, so it's going to be negative omega c times v times, yeah, sine omega t plus phi v. Okay, now again, I don't like sine. All right, so I want to change that for myself. How can I turn that into a cosine? How did I turn sine into a cosine? Subtract 90. All right, so this is cosine omega t plus phi v minus 90 degrees. Okay. All right. So what I've written here, just to be clear, do I have, all right. I've got I of t equal to negative omega c v cosine omega t plus phi v minus 90 degrees. And I've got v of t equal to v cosine omega t plus phi v. Okay. Yeah.
You can tell me how did you find IT equal to negative omega from the previous equation?
I took the derivative there. Right, so I took the derivative of cosine. Derivative of cosine is minus sine, right? And because I have omega t, the omega spits out, right? All right, so I end up with that result there. Now I'm going to write this guy here as I cosine, and I want you guys to help me out here for a second. So negative omega. I got a negative sign in front of there. Negative's an angle, isn't it? What's the angle of -1? Let's see, make Yahoo proud. If I wanted to tell you -1, that's a complex number. It's an integer, but it's a complex number. How would I write that in polar form? Wait a minute, isn't it just -1? 1 with an angle of 180 degrees, right? That is right. So -1 basically on the axis, right, points on the negative real axis, right? The negative real axis has an angle of 180 degrees or negative 180 degrees, right? So I write that as 1 angle 180. So what I'm going to do is I'm going to move, and there's a trig identity for all this sort of stuff, but I can move that minus sign inside of this thing and write this as omega t plus 90 minus 5e. And I'm going to say that I equals omega CV for a second. Okay. I equals omega CV. Okay. All right. So the heck am I doing? All right. Let's say for a minute that just to make things nice and simple, let's say omega C is equal to 1. Okay. And let's say V is equal to 1. Okay. Whatever numbers those are, that's what they work out to be. All right. So just in my example here, let's say that's the case. Now, in general, that's not going to be true, but let's just say that's the case in my example, just so we can look at this and see what it would look like. All right. If that's the case, and let's also do in my example, let's say 5v is equal to 0 degrees. Okay. So that would turn this into, in my example, all right, so this would be the example. Everything I wrote above was general. Here's an example. For this example, I'll have I of t is equal to cosine omega t plus 90 degrees minus 5e. And this guy is v of t is cosine omega t. All right. How would I draw that in time? And let's think of we'll think of the phasor and how I would draw that. So let's do for ourselves the phasors too, right? What's the phasor for the voltage? So what is, and I always kind of write that relationship with this arrow between the two. What's the phasor for the voltage? 1 angle 0. And what's the phasor for I of t? 1 angle 90 degrees. Let me write that as 1 angle 90 degrees. All right. So how would I draw the graph of I of t and v of t? Yeah.
Well, I of t is 90 degrees offset from v of t.
I of t is 90 degrees offset from v of t, and 90 degrees in which direction? Is it going to go to the cosine? You know, we should know what cosine looks like. Cosine looks like this. All right, my bad drawing of cosine, but that's cosine. Is I of t going to the left or to the right? To the left. Okay. To the left. So in this case, what I have here would be I think in my I didn't draw. Okay, forget that slide. I didn't I think what I drew there was different than what I just actually did. So so based on what I did here, I'll take that slide out of my final one, right? Here is V of t. I of t would be 90 degrees ahead, so that would look like this. Right? No. Right? This would be I of t. This is part of the reason why we also don't want to use the time domain. It's a heck of a lot harder to draw it. All right. I of t is 90 degrees ahead. Now that's a bad drawing, but how do I know it's 90 degrees ahead? Well, basically the peak here and the zero cross here, wherever when the zero cross and a peak line up, I know there's a 90-degree shift between them. All right, and that's because I know what the relationship is between sine and cosine. They're always 90 degrees apart. You may not remember that. Important thing is when I have I of t being cosine omega t plus 90, its peak happens 90 degrees earlier, meaning that it's cosine pulled over to the left. Now, in the context of phasors, right, we said that in this case, I have I equal to 1 angle 90 degrees, and I have V equal to 1 angle 0 degrees. How would I draw that in the phasor domain? So in the phasor domain, I'm drawing a complex plane. Okay. Where would V and where would I be here? Right. So yeah. So basically what I have is that V is here. V is angle 0. I would be straight up like that. All right. And there's a 90-degree shift between the two of them. Right. And so when I look at this, what did I use that term of lead and lag here. I said, so if I have a vector that's that's ahead in the counterclockwise direction, I called that a what? A lead or a lag? A lead. All right, so I is leading V, and it's leading V by how much? 90 degrees. All right, I is leading V by 90 degrees. So I can see right here very easily that the angle of I is equal to the angle of V plus 90 degrees, right? The angle of I is the angle of V plus 90 degrees. Whatever the angle of I is, or whatever the angle of V is, I add 90 degrees to it to figure out what the angle of the current's going to be. All right, that's how I get that relationship. Now, there is another piece to this relationship too, which is to tell me how do I get from the amplitude of the voltage to the amplitude of the current? Well, we said previously here on our slide, right? We said previously that, go back a couple, right? So I of t in general was omega c v cosine omega t. What did I end up with? I hate this.
Quick question about that. So
I'll get to you.
yeah, so how come, can you go a few slides back? It was like on one of the lines you had plus 5B and the other you had minus 5B.
So what I had to do here is
Because wouldn't it just be you add more?
Well, yeah, so yeah, I add one yeah, he's right. That's I don't like thinking of it like this. I think of it always in terms of impedance. You're right. This should be if I gave you, just to be clear on what he's asking, very good observant point. My brain was starting to, if I look at this guy here and this guy here, two waveforms, how much of a phase shift is there from this one to this one? How much do I have to shift this guy to become that? 180 degrees. So he's right. Basically what I did wrong there is it's plus the minus sign. Because in other words, multiplying cosine by -1 flips it over, right? That's the same thing as taking the same thing and shifting it 180 degrees. So by putting a minus sign out in front, you guys are going to get thrown off by this eventually also, because I'm going to give you something like, what happens if I have -3 cosine omega t? What's the phase of -3 cosine, or what's the amplitude of -3 cosine omega t? Not -3. Amplitude's always positive, right? If I gave you 3 cosine omega t, this guy would be 3 cosine omega t. All right, and let me draw this other one better. Something that has the same amplitude. This would be -3 cosine omega t. Right? They have the same amplitude, don't they? Right? They're just as big. Amplitude's always a positive number. That minus sign is a flipping of the cosine, but it's also equivalent to a shifting of 180 degrees. So he's correct. Basically, what I did here is so it's -90 plus 180, like that. So it becomes a plus 90 degrees. All right, that's entirely consistent now. All right, if I read it that way. All right. So good. That makes me feel better, right? So that means when I write this, this is 5e plus 90 degrees. Okay. And I think I wrote these too close together, right in front of the part. So I write this as I cosine omega t plus phi I, the angle of the current, and v of t is equal to v cosine omega t plus phi v. So a couple of things that I see about this, okay? I also said that I is equal to omega c times v. All right, and I see that phi I is equal to phi v plus 90 degrees. All right, so a couple of key results here. Right? If I do this, and I'll write it, I don't like writing this phi I. I'm going to say the angle. Okay, the angle of I is equal to the angle of v plus 90 degrees. All right, so the magnitude of this, so the amplitude of this thing, of this cosine, is the magnitude of the phasor. The angle, or the phi, the phase shift of the time domain waveform, is the angle of the phasor, right? So when I look at this, I've got some relationships here. I've got that the magnitude of I is equal to omega c times the magnitude of v, and the angle of I is the angle of v plus 90 degrees. So what I want to do is instead of writing this is basically two equations here, right? This is an equation for the magnitude, this is an equation for the angle. I don't like having two equations. With complex numbers, I can put them all into one equation, can't I? Couldn't I say this? Couldn't I say that I, the phasor, is equal to j omega c times v, the phasor? Okay, I could say that. Now, let's check to see if that makes sense. All right, so this is, so in other words, this is compactor, right? It's smaller, right? Because this is two equations, right? This isn't one equation. It's two equations, right? What are the two equations that come out of, so I have complex number equals complex numbers multiplied, right? That's two equations. What are the two equations that come out of that? One for the magnitude. I guess there could be four, I guess, right? There's one for the magnitude and there's one for the angle. There could be one for the real parts. There could be one for the imaginary parts. So if I took the magnitude of both sides right there, the magnitude of I is the magnitude of I. The magnitude of V is the magnitude of V. What's the magnitude of j omega c? What's the magnitude of j omega c? So j omega c is 0 plus j omega c, isn't it? So if I said, what's the magnitude of that? What is it? Omega c. Can't have a j ever in a magnitude, right? So it's just the omega c parts. The imaginary part becomes it, right? So the magnitude, so what I see is that the magnitude of I is omega c times the magnitude of V. This is an angle relationship, right? So I have complex number equals complex number times complex number. So if I have one complex number times another complex number, how do I get the angle? You should know this. Don't Yahoo cries at night. He does. What's the angle relationship here? I add the angle of j omega c to the angle of V. So what's the angle of j omega c? Oh, you guys are thinking, oh, what's the arctangent? What's the angle of 0 plus j omega c? The angle of that.
Tangent of the imaginary of the real.
Well, that's not going to get you too far. It's going to get you put that in your calculator, you're going to get not a number. Right? You're right. That's an approach, but you're going to get not a number here because it's going to be arctan of something over 0. Another way I can think about this is draw it. Draw the vector. Where's it going to be? So if I give you 0 plus j omega c, where would that be? Pointing straight up. So the angle is what? 90 degrees, right? So this guy would be, if I did the angle relationship, the angle of I is equal to 90 degrees, which is the angle of j omega c, plus whatever the angle of V is. In other words, this relationship here gives me that complex number relationship, I equals j omega c times V, gives me the same results I got from doing the time domain stuff. And what I do is I call this here, if you look at this relationship, it's got a nice form. It has I equals something times V. Well, that's awfully similar to something we've seen before, right? Where have we seen I equals something times V? All right, you're used to thinking of it as V equals something times R, right? Or how, so what is that? If I gave you V equals IR, that's Ohm's law, right? This guy is basically Ohm's law. But instead of R, I call it Z, right? All my Z's are always going to have a little line in the middle of them, right? That Z term is what I call impedance. And for this particular capacitor, it's 1 over j omega times C. All right, is what that guy is. So it tells me that what the heck is the J doing here? Because I like imaginariness. I don't like imaginary. You guys don't like anything. You guys don't like things that are real. You certainly don't want anything that's imaginary, right? So why am I using the imaginary number? What's the point of using it? What's it helping me do? Not to do, yes, well, that's good. And I don't have to do differential equations. It's tracking for me the angle shift, right? The J is a 90-degree shift. Multiplying by J is a shift by 90 degrees. All right, and so it is capturing that 90-degree shift. And so basically what I've got is a new version of Ohm's law here. V equals IZ. Now, for an inductor, same thing. All right, we're going to see that on Monday, right? But basically what I've got here is everything that I need to know in steady state is captured. If I use imaginary numbers, it allows me to capture that phase shift business. Okay, and so the imaginary number turns out to be incredibly useful because it lets me avoid the differential equations that suck. So, right, so we trade weird for suck, or suck for weird, right? I guess I should be careful about that. All right, no differential equations involved if I go this route. Okay. All right, I will stop there. And we have recitation today.